So I want to talk about an interesting op-amp circuit. And we've kind of been talking about a number of things where we may have resistive feedback for both inverting and non-inverting configurations, as well as being able to take a differential input and get a single-ended output. We've talked about capacitive circuits, where we can actually do gain around an amplifier using capacitors. And of course, we still have a charge at that node that will determine the circuit, and that can be sort of a plus or a minus. But I want to talk about this in terms of a practical example that you see used particularly a lot in the last, say, decade or so in terms of looking at really small voltages, say particularly in a neural amplifier or neural front end or other kinds of very, very small signals, where I'd want to be able to take a differential input and look at the output voltage. But I want to be able to do this entire circuit, say, on an integrated circuit. Because the integrated circuits, typically capacitors are easy to find. Resistors are actually hard to do, except for some interesting device level properties. This is quite common in terms of neural amplifiers. The name typically associated with this is Reed Harrison and his work almost, the time I'm recording this, almost 2 decades ago. And it's really quite straightforward because if you look at these structures, you see the capacitors, and you see I've got this combination of a resistance and a capacitance and a large resistance. So I have an input and a feedback terms, what I would expect for a differential configuration, which then gives me this particular output response. It's a high-pass response where we have a particular time constant. We'll typically try to get that time constant to be like less than a hertz, so that way I can get like most of my signals through, but I still can like adapt to any like weird changes in the environment. And if you're dealing with lots of, say, neural measurements, you're going to see a lot of weird changes in your environment. And so you want to be able to kind of be resilient against these things. The large resistance is primarily there, so I don't have to worry about any charge settling. But certainly from the original time of designing the structure, it was definitely thought about in terms of a capacitive amplifier, much like we might imagine around an op-amp, but then going, how do I not have to set the charge in a difficult way? And just putting a huge resistance, maybe with a device property, is how you would think about it. And so this is kind of how you begin to look at this. Now, of course, when you get to higher frequencies, this high pass just turns out to just be C1 over C2 times the difference of the two inputs. And this can easily give you a really nice gain stage of around 100 or so, 100 to 150, 200, easily on chip. There's some other advantages if you get into more specifics of some of the op-amps, particularly because the capacitors don't add noise, and the large resistances have very little effect on the noise profile. So this gives you a really interesting circuit, but we've been probably talking about lots of linear circuit kinds of ideas. This is one where you would actually see it being used in a multitude of applications, and likely is in instrumentation that you may end up seeing someone use in the near future.